introduce, describe the results produced by variation and assimilation, mostly for Ivan. Pavel has already spoken about Bolivar. We have already interested in the various things which will be for me. So, I remind you of the stage which we have reached yesterday. My way of presenting things. A typical situation, what occurs most of the situation which obtains most of the time in our applications. We want to estimate the state vector x, which again describes, typically, is the description of the state of the flow at a given time. It doesn't have to be that. Most of the time it is that. And that is, more precisely, the numerical values of all meteorological parameters, and in practice that is the two components of the horizontal wind, temperature, or another quantity, humidity, either global humidity or humidity in its three phases, that at all wet points in the volume in atmosphere, plus a number of variables at the surface of either the ocean or the continent, in particular surface pressure. Numerical models, numerical weather prediction models are based on approximations, in particular hydrostatic approximation, which makes that it's fundamentally sufficient to specify the quantities I've just mentioned to describe the state of the fluid. So x is, I'm not going into full details, x is a big one, a number of numerical quantities which are the values of all relevant meteorological variables at all wet points of the model. Is that clear? And then, at a given time, we have a first estimate, the background, which typically is, again, it doesn't have to be that. I will illustrate that on the chart in a few minutes. It doesn't have to be that. But typically, it is a forecast which comes from a recent past. And then, there is an additional set of observations which come in. And what we want to do is to update the background with the new set of observations. And the observations are related to the real set x through an operator, which here I suppose to be linear, that is, which can be represented by a matrix, which is denoted x. And both the background and this additional set of data are affected by errors which are not known, about the statistical properties of which we will make hypothesis, and which have been noted here, zeta b, b for background, and epsilon. I come in a few minutes, I'll give an example, but here, in particular, one of you has just asked me to be a little less abstract in particular, to describe more precisely what H looks like. I will do that necessarily. But again, I'm saying, we assume that statistically zeta d and epsilon, the errors, have zero expectation. And if I don't have, it is necessary to know what those expectations are. I'm going to subtract those expectations from the data. What the real hypothesis there is that the expectation of errors is known. And we assume that zeta d and epsilon are statistically correlated, which is a strong hypothesis, but in a sense, mathematically, it is not restricted. And then we give names to the covariance matrix of the zeta D PB, often given as B, but I call it PB, and the covariance matrix of epsilon, the error is called R. When I gave you, I showed you the formula, which also in, so you can filter as Pavel shown, that we have a characteristic XA, which is equal to background, plus a gain matrix, which depends on PB, on pH, and R, times the innovation. The innovation is different between the observations, and what the background predicts for the observation. And then you have a new covariance matrix for the estimation error, for the analytic error, that is an error bar on the analysis, which is the covariance matrix for the background, and minus something. And pardon this presentation, wrote that some equation in slightly different form, which is PA equals the identity minus PB. Did you put PB as a factor in front? Or in,
no, minus KH.
Minus PH. PB, that's right, minus PH PB, where K is the gain matrix here. Yes, minus, it can be it's just equivalent to that. K being the gain matrix. That is the same part. Okay, so now for something which might be a little the scanned figure. So it's not very easy to read. I'm sorry for that. But this is meant to illustrate what I just said. So this is the background. This is an X. It's a little introduced at the European Center for Medium Range Forecast, whenever I'm going to go. It is the forecast of surface pressure and surface wind, or 10-meter wind, in an area which is not obvious to identify. It is actually the northern Pacific. You can see here the coastlines. If you look carefully, you will see the coastline here. But Alaska, and here there is the Aleutian Peninsula, and the Aleutian Islands. The coastline goes on this side. And here there is the Bering Strait, and here you have the coast of Siberia. Not be absolutely obvious, but here you have the Kamchatka Peninsula, here, and here you have the Okhotsk, I think that's say in Russian, the Okhotsk Sea here. And so this is the forecast for surface pressure. There are isobars, which is here, and there is a depression. There is always a depression in this area. The Aleutian depression, which is actually the most permanent feature in the atmospheric circulation. If you look at the European maps, there is always a depression in the Aleutian. And so this is the forecast. Unfortunately, it is not very easy to read, but believe me, take my word for it, the isobar, which is here, corresponds to 960 hectopascals. Like the value of the predicted depression. And there is also predicted wind, represented by arrows. This is the background. 6 hours. Yes?
When you convert this into a column picture, does it matter the order you put the variable?
The order is everything. Actually, it's never converted to a column. These variables, we write that as a vector for the sake of describing what we do, but in the computer, all that can very well be in different arrays. It's different, the arrays for wind, the arrays for surface pressure, and they don't have to be in one column. Just as the matrix H, I'm going to speak about a little more, the matrix H doesn't have, there is never in the computer a two-dimensional array which is the matrix H. Actually, most of the time, the matrix H is full of zeros. So filling in an actual two-dimensional array of the computer with matrix would be absurd because there will be mostly zeros in it. We introduce matrix H for writing an equation in a compact form. Actually, describing the code will still be much more complicated than introducing H explicitly in the equation. No. Okay, so that's the background. And on top of that, there are observations. That is why. You don't see them well. For instance, here there is an observation of surface pressure. Value 957. Believe me. Demonstrated. So, actually, according to this observation, the depression is deeper than predicted in the background. So the innovation, which is the difference between the observation and the background, here is multiplied, is about -3 hectopascals for that particular component of the innovation. And there are observations. There is an observation of surface pressure also. Here, which goes together with an observation of wind. I'm going to speak about the observation of wind. And that's, I think, I don't even remember, 61,000, but it's 995 hectopascals, and the value here is 995 hectopascals, and the value here is 990 hectopascals. So again, there is a small depression here, which is denoted with a letter L, and according to this value, compared to the isobar in the background, the depression here must be deeper than predicted. And there are also observations of wind. But there are exhibited here. These are written by those without observation of winds. They are not in the same format as the predicted winds. The predicted winds are just vectors. The observation of wind are written in a slightly different format, are plotted here in a slightly different format. Something like that, with little bars here. This dates back to the time, the pre-computer time. In pre-computer time, as I told you yesterday, the basic working material of meteorologists consisted of charts drawn by hand. And if you rely on the length of something which is written by hand to measure the intensity of wind, that's not very convenient. You have to have it quantified, to do it by hand, already quantified. So, format of written hand-drawn charts to represent a wind observation by a bar whose length was irrelevant, but the direction of the wind here, the somatic the wind is going in this direction. This is observation point, and the condition was that the wind, or the bar was drawn in the direction the wind is coming from, like the east wind coming from the east. And then there were a number of little bars added by hand, which indicated the intensity of the velocity of it. There is a code. I don't know it. Maybe I learned it at some time. You can write it. You can read it here. It is there. You have two. You have here two observations of winds, which are at quite an angle, about 45 angles, with a predicted y, with a predicted wind. So the innovation here, I don't know when the intensity, but the direction of innovation, which is that case, is vector, because it's the difference between an observation and a prediction, at angle 45 0, 45 0. And here also there are winds. Here, interestingly, there are two measurements of winds, which are almost perpendicular to the isobar, the corresponding isobar. which is totally contrary to geostrophic balance. Geostrophic balance has it that the wind basically follows the isobar. As it is about here, you see well here, that the wind is rotating, there is a vortex around the depression, in the sense which corresponds to depression in the northern hemisphere, with a slight convergence to the center. So the wind does not exactly follow the isobar, but it is at a small angle with the isobar, with convergence toward the center of the vortex, which is normal at low level. At higher latitude, the wind will be almost parallel to the isobar. But here you have two wind measurements which are at a right angle with the isobar. And that's totally contrary to geostrophic balance. Well, actually, in that case, it's not difficult to understand why it's there. This is the Kamchatka Peninsula, which is the mountainous area. And this is the surface wind, which very likely flows down the valley. And so there are mountains there, and the wind just flows down the valley. And I presume that the model, that version of the model that's old, didn't have a description of those mountains. So it is not surprising, but the observation for this is something which is totally at odds with the forecast. But it's normal, because that wind probably is due, those winds probably are due to valleys, to mountains which are not described in the model. So the model cannot guess out there are mountains there, because it has not been informed of the existence of mountains in the first place. So, that's HB, and the observation are plotted. There are observations, there are winds, there is a wind observation here, one here, there are wind observations here. These are rather good arguments for positive in terms of direction, and you can see in terms of values. And so the innovation vector, what's D, consists of all these differences between observation and forecast. But again, the innovation vector will never be put in a column in the computer. They are just values which are stored in various arrays. There is no need. Concerning the operator H, the precise question was asked in this point. Let us suppose, so, the operator H, as written on the previous slide, for a minute. Slide. It looks as if it is a matrix operating on the whole state vector. Whole state vector will be something like that. And there is a matrix of coefficients, and here there is the vector y of observation. It looks like something like that. I'm sorry, you can see well from the stuff, but that's all I'm going to do here. An operator H, which acts on the whole state vector, which is x, H, and this is vector y. I stress again that there is no need of any relationship of any kind between the dimension n of a state vector and the dimension p of, which is the number of observations. It's the absolute thing here. In particular, the number p can be smaller or larger than n. It's totally irrelevant. So this in general will be a rectangular matrix. But absolutely no reason to assume it is a square. It actually makes no sense. In any case, they are not in the same space. I mean, it's a square with coincidence. So actually, there are a number of individual scalar observations. So writing that as a matrix equation is just a compact way of writing things down, because we have a number of individual scalar observations, and what matters is simply how those individual scalar observations depend on the state of the flow. So, actually, writing that as it is here and there is only a compact way of writing things down. It has no other significance than a convenient description for avoiding to fill entire pages of paper or blackboards with hundreds of individual scalar equations. It's just a compact way of writing things down. It has no particular physical significance. No. It's just a way of writing things down. What is significant is how one individual observation, what is physically significant, is how one particular scalar observation depends on the state of the flow. That is significant. And that is expressed by a number of coefficients along the corresponding row of metric H. But there is no connection between the different rows. It's just, writing things, a list of things, and I have a list, I call it a matrix. But it's only a list of a list. Each row is significant, because each row expresses how the particular corresponding scalar observation, physically or statistically or both, depends on the state of the flow. The relationship expressed by the coefficient along one particular row of the H matrix can express physical knowledge or statistical knowledge, or both combined together. Okay. So what is it, H? Let us suppose we have observed one quantity. Come back to. We observed one quantity, surface pressure, at one point. Let us assume that point coincides with a grid point of the model. There is no particular reason to assume the case. Let us suppose that here in X we have everything, the wind component, which are formally written by Z, just again for convenience. But somewhere in there, there is a list of surface pressure, of model surface pressure at all those points. And I say again that in meteorological models, in weather prediction model, as they use at present, these models are built on the hydrostatic equation, that is on the hypothesis physically to what the pressure at a given point is directly proportional to the weight of the air above that point. Since correctionally, Galileo correctionally, and Pascal, we discovered the extraordinary things that air has weight. So in that case, we have somewhere, that's totally formal. I mean, in the computer, it's not even like that. I mean, somewhere, surface pressures. And then the corresponding line will be, since we have observed surface pressure at a given point, the value here is just the value to be put in Y is just to be put in just surface pressure at a given point. So the corresponding row will be consist of 0 and then 1 at a particular along the column which corresponds if this is in my vector X, the grid point surface pressure at this grid point is number 4,923, then along column 900, 3,023, there will be a 1, and then elsewhere it will be zeros. Observe what it will be. Of course, I will never fill in a two-dimensional array in the computer with hundreds of thousands of zeros and 1 somewhere. I have a code which just tells me that what is observed, the observed pressure at a given grid point. Actually, all those matrices you saw in these equations are almost never stored as such in the computer. What we have are codes which are able to produce to make the computation, multiplication of the matrix with a vector. There are code which do that. But the matrix is in the form of a code, not in the form of an array. And if, as is more reasonable, the observation of surface pressure does not coincide with the grid points, then what we do to go from the model to the observation point is to do some average, which might be based actually on an optimal interpolation. But we compute, take the surface pressure at a number of neighboring grid points, and for these values of the surface pressure at grid points, we obtain a value at the observation point. The scheme to do that could be an optimal interpolation, which I described. And so the corresponding line would not be 0, full of zeros, and then 1, 1 somewhere. It will be full of zeros, and then a few coefficients, which add up to 1. In that case, it will add up to 1, at a few grid points. The grid points which are close to the observation point. So this is what formally the matrix H would look like, would be. But again, it's never stored. You consider as a two-dimensional. So these are for rather simple observations, in a sense, which bear on the same variables as the variables which are used in the model for describing the state of the atmosphere. But there are more complicated observations. In particular, there are, and more and more, radiance observations. That is, observation in a given wavelength of the infrared flux emitted by the planet towards external space, which are measured by radiometers on board satellites. So what it is? Well, the infrared flux, the intensity of energy, which is measured essentially in watts, is a complicated function for what is called the radiative transfer equation of the temperature and actually also humidity profile of the atmosphere at the position when the observation is made. And I can write like that somewhere in my file, the so-called radiative transfer equation, but the radiative transfer equation is basically expresses that each layer of the atmosphere emits radiation both above 0, essentially, not exactly according to sigma Stefan laws, sigma is the Planck laws, sigma absolute temperature at the fourth power, with some coefficient into account. Well, it's rather complicated. And this emitted radiation can be transmitted up through the atmosphere if the atmosphere is totally transparent to the particular one, then up to the satellite, or can be reabsorbed in its way, and then there is a global A, and then if this is reabsorbed below, the layer will re-emit emission to Earth. And all that is described by what's called a radiative transfer equation. And that's not trivial. I mean, it will take almost a whole school to describe all that. It's done, and it is in the numerical models. It is in the numerical models. And it is there not only for our simulation, it is there because it is necessary anyway to compute in the model as such how much energy the atmosphere absorbs and emits. It is necessary to compute the equation, because there is an energy equation and a budget of energy, but it is necessary to compute how the temperature varies at every point of the model in the course of the model integration. So this equation is there. It's there in the model anyway. Not particularly for computing exactly what a satellite observes, but it is there to compute how temperature varies at every point of the model, at every point of the model. And then it is slightly modified with an additional computation to to compute what a satellite would observe in a given wavelength. So, once we do that, and we linearize the equations, for instance, in the visit of the background, linearize, and so on, what will you observe in a given wavelength in the infrared spectrum by a satellite above a particular point in the atmosphere, in the surface of the Earth, will be, I call it y radiance. So radiance means in a given wavelength, and here, you can see it's part of y radiance. So this means in a given wavelength of a spectrum and at a given geographical point equals summation of temperature I, Ti, plus humidity Hi, with coefficient alpha I and beta I, where the Ti are the temperature on the vertical at all model levels on the vertical at the procedure points, and Hi are the humidities. And so what H contains, in terms of its observation, is typically the alpha I's and the beta I's for those columns in the matrix H, which correspond to where I've decided, and that choice the decision is totally arbitrary, where I've decided to put the temperature and the humidities at the good point above where the measurement is made. Again, to answer one question, the order in what this is made is totally irrelevant, and it is all the more irrelevant that actually it isn't done in the computer. The computer will never put an order in that. There are observations, and we deal with them. We never rank them. It's not done. It's done only when it comes to writing down equations in compact matrix vector form. So that would be, for that radiance observation, the content that would be alpha 1, alpha 2, beta 1, beta 2, and the appropriate columns. Of course, this assumes linear relation, and I'll think about that later. And of course, also, in the observed radiance, there is something which comes from the surface, either of the ocean or the atmosphere. And of course, it has to be taken into account, either subtracted or something. You have to want special care about it. Yes?
Yeah, so far the derivations of optimal interpolation and the best linear and unbiased estimate, and also in Havel's derivation, I still haven't recognized why H needs to be linearized. Should one just take the nonlinear radiated transfer equation?
Yes, well, actually, as I'm going to say, in variational simulation, H is not linearized. We take a nonlinear H, and when we do minimization, with the nonlinear H.
Yeah, this is the innovation vector.
Again, I've written that to be consistent with the approximation which is in the equation that I've written.
Yeah, and then my question is, why do we need to make that approximation?
We need to try to explain. Okay. Because, why is it necessary to do it? Because what we do still, most often is an extension to nonlinear cases to the blue. So in order to explain the method we use, I find it easier to first explain the linear theory, which requires a linear H and a matrix, and then to say, that's what we do. In practice, we use nonlinear H, and if it is not too much nonlinear, it will be a satisfactory approximation. I explain how that is done in variational simulation. But it is true that when I speak of a linear H, I don't even describe what is actually done. At least in variational simulation, it is only a simplified description I gave in order to make things, not to describe everything at once, which might be a little too complicated.
In the blue case, you also take the H matrix and multiply it by the PB matrix, and then you invert that. So,
Yes.
so is that just a way of writing it, and you don't actually do that?
Well, it depends on the scheme. There are schemes in which that was actually done. In traditional assimilation, it is done through minimization, which in the strictly linear case would be exactly equivalent to do the inversion of H, PB, H transpose R, but we don't in traditional assimilation do the explicit inversion. We do a minimization, which in the strictly linear case would lead to the same result as doing the inversion. Actually, what we can do, it can be said that we do the inversion by an iterative process, by minimization iterative process. To take a simple example, let's say you want to solve the equation Ax equals b, well, A is the I square matrix, X is the unknown, B is the non-vector. You can do that by minimizing X minus B squared. You can do that. By looking at the X, which minimizes the function X psi minus B modulus squared. You do that. And you use an iterative algorithm to find the minimizing sum. That's X. When doing that, you do not explicitly invert the matrix, although the final result is the same as you would obtain when you invert the matrix. It's, in a sense, once we do a variational assimilation, we do a Okay, so other questions about the H matrix, because you write it before the matrix. Actually, it's not even right. But other questions? Okay, so I come back to that. And now I go to the panel on the right, which I haven't commented yet. The panel on the right is XA. That is XB, that is XA. Once the observations have been taken into account through a process which at that time was very close actually to the linear computation XA equals XB plus various XA equals XB plus gain matrix time Y minus XB. And so what has happened? So again, believe my word, take my word for it, because you can prove the value. Here I plotted a superspatial observation of 957 hectopascals. Now I knew, so this said, the predicted depression is not deep enough. So okay, I'm given the depression. And a new isobar, value 955 hectopascal, has been created in between. And the 957 hectopascal observation is there. It's not at a distance of 2/5 between 1957 and then between 1955 and 1960. Because the observation is affected by error. There is an epsilon and an R matrix. So the system knows it has some leeway for not adjusting exactly the observation. Actually, it takes a compromise between the background and the observation, a compromise with weights, which are essentially in inverse proportion with specified and specified error variances. It is not exactly as simple as that, because the other values also impact. I said that there was an observation here, which also said that the depression here was not deep enough. Okay? That's the same as introduced a new isobar to deepen the depression. And the observation is at 995 hectopascal, bear with me, and this is the contour line, 995 hectopascal. There is not exact coincidence, because again, the system knows that the observation has not to be taken literally. There is some leeway about it. There were here two measurements of wind, which I said were at an angle for predicted wind. Now, the analyzed wind, is parallel to the observation. The correlation has been made. And there were two measurements of wind, which are at a right angle with the predicted isobar. Still at a right angle with the predicted isobar. I suppose, I don't know. Nobody will ever know, I think, because, of course, not the observation files, but the code for doing the simulation of the most, and nobody will ever rewrite this course code. Actually, it's pure nonsense. Right. So nobody will ever know, I think, but presumably the system was informed that these local observations were due to local orographic effect, and told analysis ignoring that if such a provision was in the code, that would be recovered. That hasn't been lost. That has been written down somewhere in the description of the system. And actually, the people who developed those codes are still around. I mean, Andrew Lawrence, I don't know whether he developed a particular piece of code to supervise the writing of the code, is still around, and I think you will be able to tell. But whether on that particular case these observations were or not, I don't know. But it looks as if there were, and if my prediction, which I'm not sure is correct, is that the local observations are due to local orographic effects which are not present due to mountains which are not in the model, it was perfectly legitimate to ignore them. They induce physical effects which are real, but which the model doesn't describe. Okay, so this shows how one goes from an XB, the background, to an XA using a number of observations through essentially a formula of this type. Okay. So, other questions? If questions come later, we can come back to this. We can come back to this. Okay. So, what was in which we implement this kind of thing? Simplified in a sense. Simplified to make things intelligible, reasonably intelligible, I hope, and also to be able to write down formula in the compact form. So, these are the formula from the two. And so, yeah. But before that, anyway, there are only 15 minutes of time to do. I'll come back to my elementary example. We want to determine a scalar quantity, x. Now it is a scalar quantity, and we have two observations, z1 at x plus zeta1, z2 at x plus zeta2. And in what I said yesterday, I suppose z1 and z2 are known, x is unknown, zeta1 and zeta2 are unknown, but we assume that zeta1 and zeta2 are distributed according to Gaussian probability distribution. That is, the probability that zeta1 equals to value zeta is proportional to exponential minus zeta squared over to S1. Then the probability zeta2 for some value zeta is proportional to exponential minus zeta squared over to S2. And that's S1 not necessarily equal to S2 because it would be much too easy if S1 equal to X2.
Should be less than.
What do you say?
Should be less than. It's not two.
S1, S2?
Probability of zeta1 less than 2.
No, it's a density. The probability, no, it's not a cumulative distribution. It's a density. Well, strictly speaking, yes. No, you're well. Okay, I told you that. That's it's a density. Okay, so. And I said that we do Bayesian estimation, and we found that the conditional probability for the x equals psi, given Z1 and Z2, was the Gaussian probability distribution, well, proportional to exponential minus 1/2 of psi minus xa squared over s, where xa was a weighted sum Z1 and S1 normalized by S, 1 over S, well, 1 over 1 over S2. This is what I said. So this is the weighted average of Z1 and Z2 with a larger weight given to the piece of data which has a smaller error. Which is very natural. So it's a weighted average. Now, that's an Excel you can find by just minimizing. I asked what is, consider a value psi, and I measure the misfit, whatever it is, between psi and the observation by taking psi minus Z1 squared plus psi minus Z2 squared. But since the two observations, the two pieces of data, the two pieces of data don't have the same accuracy, it is normal to give in this quantity, which is meant to measure the misfit between a psi and the two data, to give a larger weight to the piece of data which has like a higher accuracy, that is a smaller error. So I read that with weights proportional to 1 over S1 and 1 over S2. I call this a function of psi, 0 psi, and it is one measure, infinitely many possible measures, of the misfit between psi and the observation and the data. I know for psi which minimizes that. And what is it? It is the same one as this one. But psi which minimizes that is this xt. Insanity, when I say that, I don't introduce any Gaussian hypothesis. I could do that simply knowing both variances. I compute this quantity, which is very natural to introduce. Someone who does not know anything about meteorological, about theory of estimation, but who has some basic mathematical knowledge, some basic mathematical training, could very spontaneously write something like that. Yes?
But if it is not Gaussian, the weights S1 and S2 doesn't make sense.
If it is not Gaussian?
If it is not Gaussian, then the variance may not really make sense.
Variables. There are probability distributions which have a finite variance and which makes sense. And in any case, physical information can come with an error bar, with an estimate of uncertainty, a quantified estimate of uncertainty. And this is which quantified estimate which I can put there, even if it's not strictly a variance of a well-defined probability distribution.
So if it is not a Gaussian, we just use a different kind of weight.
No, if you're not, well, I don't know the system in which, I don't know the probability distributions in which this could, in which the estimation would be reduced to minimization of an objective function of this form with a weight which would not be the variances of the error. There will be other estimations, but will not reduce to simply minimization of an objective function.
The example you were giving yesterday, the exponential PDF.
Yes.
There itself the variance is not a good measure of the.
Yes. Actually, for estimating it, when exponential PDF, I assumed that the two observations were equally accurate, were the same, and that if you do that, if you minimize, you obtain the right correlation. But it is true that in that case of the exponential explanation, if I assume different accuracy of the two pieces of data, different values of what I call A, like the example, then the expectation of a conditional probability distribution would not be given by this expression. But it wouldn't be given by, I think, by another expression of this form with different values of the denominator. It wouldn't be given by a simple expression. Okay. It would, of course, be given by minimization or something, because the expectation of a probability distribution is the variance minimizing estimator of the probability in any way. So you can take the variance minimizing estimator. If you look, you have a quantity which is distributed according to probability distribution P of X. Quantity X. And you look at one estimator which minimizes one estimator or one estimator X state, which minimizes the expectation of. Okay. You take quantity X minus the real value X, right? Square. You take the expectation of that. And, no. So you take a random variable X. You take a random variable X. And you look for a quantity which minimizes A minus X squared and expectations. X is random. A, which minimizes that, is A equal expectation of X. So, in the problem I consider, the minimum that I obtained minimize this quantity for the probability distribution being the conditional probability distribution of the angle given the observation. But it is not that expression, in the case of exponential example I consider, is not of that form. It's not quadratic. It's much more complicated than that. But it exists. It exists. Still, it corresponds to a minimization of a function which is not quadratic.
You're essentially saying a quadratic cost function will always exist.
What do you say?
You're essentially saying a quadratic cost function will always exist. Yes.
Invariance of the quadratic cost function will always exist. So, again, now I come to a point, we'll be at the end of my presence of this morning, which mostly will have to the end. So, this XA here minimizes this function here, the scalar function, which is a function of point psi in state space. So psi is a model state, and I consider the space of all possible or impossible model states. Mathematically possible, but impossible. And for that model state, I compute the matrix on the one hand, the matrix between psi and the data. And the data consists of the background on the one hand, and then the observation y on the other. So I take the difference, psi minus hb minus psi, and I square it. But in order to square it, I put coefficients. And it is obvious I put coefficients, because in xb, there are temperatures, there are waves, there are surface pressures, and I cannot add them like that. I must have waves, I must use waves, which makes that I can add them. And the very natural choice is precisely to take here the inverse of the covariance matrix associated with the error on xb. Why is it reasonable? First of all, taking these waves automatically ensures that as here, a larger wave is given to this set of data, to components in the background, which I assume to be more accurate, and a smaller weight, two components which are assumed to be less accurate. It's resolvable anyway. And in addition, taking PV minus 1 makes this quantity physically non-dimensional, as is obvious here. Because here, S has a physical dimension of x squared. X squared. So this quantity is physically non-dimensional. Of course, here in that case, the two terms the thing was built in such a way that the two terms, in a way, the two numerators have the same physical dimension. But it is clear that with something like that, I could put surface pressure there, divided by variance of surface pressure, plus temperature there, divided by the variance of the temperature. So I can add up quantities with different physical significance and different physical dimensions. So I obtain a quantity which both by weighting this xb minus xi different with the inverse of the covariance matrix of the error associated with xb, I obtain a quantity which both gives a larger weight to those components of the Van Round which are supposed to be more accurate, and a smaller weight to those components which are supposed to be less accurate, and I obtain something which is physically non-dimensional. So I can mix together all kinds of physical variables without having to care that this unique and hectopascals and Kelvin and so on, and all that is totally eliminated. And same thing for the observation term. I measure here the square differences between the observation and each side, for any side. What is the misfit between y and the observation that would correspond to the step side, weighted by inverse of the covariance matrix of the error, of the assumed error on the observations. And I add up these two terms, which obviously amount, and I add up these two terms, and then I find the side which minimizes that, which obviously is trying to find a compromise between two requirements. On the one hand, being close to the background, within the margin of accuracy defined by PV, and to be close to the observations within the margin of accuracy defined by R. And I minimize that. And what do you obtain? The same X I showed you before. Then this. Then this X here. You can do that easily. You can write down this involves matrices, not even very difficult. Find out the psi which minimizes that. If you do that just algebraically, you will not find this expression. You will find the equivalent expression I showed yesterday. Equivalent expression I showed yesterday, and which Pavel also showed this morning. Which is this expression. The gain matrix, right, is not the same. I told you these are equivalents. There are several ways of making their equivalents. Either by direct matrix algebra, or by more fundamental argument, so both formula must lead to a variance minimizing estimate. One variance. So if you minimize the function j of psi, which if you minimize that function, J of psi. So it is often called the cost function. The word cost function comes not from meteorology, but from estimation theory. Mathematicians and applied mathematicians who developed mathematical theories and methods for optimizing things like this, finding the value of given parameters which have some form of optimizing property. And in the first, I call that cost function because the number of situations, the quantity they wanted to minimize, was actually a measure of the financial cost. But little by little, it came to application in which the quantity which they wanted to minimize had nothing to do with any cost in any reasonable sense of the word, and they decided to shift to the least committing word expression of objective function. This is what I will use, and incidentally, I mentioned yesterday a paper by Calliope and others in which notation and vocabulary are recommended for simulation, and they do recommend objective function, although actually it doesn't pass into the vocabulary, and still cost function is very much used. But I will use objective function, which I personally prefer. This is not associated with the cost, a financial cost or a cost in meteorology, for instance, nothing to do with the financial cost, which would result from an erroneous estimation of the state of the atmosphere. Of course, can be financial cost. But this is not, cost is not measured by such a quantity. So, variational assimilation, I should say variational analysis at this stage, because there is no time dimension, there is no temporal dimension, amounts to computing XA by an iterative minimization process which progressively determines the quantity which minimizes the function. And another form is called 3D or three-dimensional variational assimilation analysis. I mentioned that it is used operationally for operational weather forecast in the 3D form in a number of meteorological surfaces in the US and most of the time in China. Not up to date about who is doing what exactly. So, and of course, that can be used, I don't know, in common filter, which Pavel described. The analysis phase could be implemented by minimizing the function of this form. So, I will stop at this point. Okay.
Just a minute. The variable psi is actually a function itself.
The variable psi is a model state. That is, it is an ensemble of values of all meteorological variables at all points of the world. So you can call that a function.
So in that sense, the cost function is actually function of a function, so it's a functional.
Yes,
so the minimization here actually is in function space.
Yes, well, although in practice it's always before time.
Sure.
It is always before time. The final purpose is to estimate meteorological fields, and even meteorological fields which are continuous functions of spatial variables. And yes, the ultimate purpose is to find meteorological fields, of course, to be always the fantastic.
Is it possible? In some cases, I actually know in seismology, actually they say the convexity is too low. Instead of considering, they define different mystery. For example, like the traveling time. So I'm just wondering, is there any good way to increase the convexity of the mystery?
To increase what?
The convexity.
Oh, I'm going to explain the condensity of the function. Okay. Yes, well. To cite briefly, that purpose in practice is essentially achieved through this term. This term, which is called, in meteorological jargon, this is called JB, G for phenomenon, of course, and GO, O for observation. People who do that will speak of their GB, GO, implicitly assuming that everyone in the audience knows what a JB is and a GO is. Assimilation operation, as any specialty, has its own jargon. JB and GO belong to a jargon. But what you said is, in practice, essentially achieved by the GB term. But there are cases in which additional term intended as increasing the complexity so as to make the minimization easier are added. Yes, that's a very general feature in optimization. People who want to minimize something, and for many reasons found that minimization is not efficient or very difficult to perform numerically. So the terms which are meant to make things easier. In some cases, it is purely numerical. In our application, it is essentially achieved by that term, which, as I said, has some critical significance. So actually, this problem of convexity, I think, is not as serious in our application as it is in other applications. Yes. The blue is exact. Well, in linear, if H is linear, this is exact. If H is linear, the quantity which minimizes that is exactly the HA, which that's absolutely exact. Now, this can be used from practical and heuristic point of view with an H which is not linear. We can still try to minimize that with an H which is linear, and numerically we can try. And actually, when H is not very strongly nonlinear, this works. But then doing that is going out of the basic theory of blue, which is still at the basis. It is a heuristic extension to nonlinear cases of a theory which is exact in the linear case. And of course, this is the kind of thing which exists everywhere in science and technology, but in extending, especially since computers have been available, extending the numerical approach, which is based on a given theory valid in some limits, to situations which are out of those limits, the kind of pragmatic and heuristic extension that's everywhere in engineering. In particular, in the engineering of data computation. But in the linear case, the H is linear, minimizing this quantity produces the X in the blue.
Exactly.
Yes, exactly. Okay. Well, so
Good enough there. We have lunch now.